in this course, the complex numbers play a very central role. So we will start by considering a different way of viewing the complex numbers. Remember, the traditional way is to consider the complex plane here now with two axes, here, the real axis and the imaginary axis, and then every complex number is represented by a point in this plane then. However, the different way here now, which I'll introduce, is the following. Maybe consider this plane now to be a plane in 3 space. So I have sort of drawn this plane here as a plane in 3 space. And then imagine we have the origin here. And then we draw a sphere with radius 1 around the origin then. And then we take the north pole up here, which will be the point with coordinates 0, 0, 1. And with this setup now, there is a very natural way of identifying points in the plane with points on the sphere. So if I take this point here, for example, then we can draw a unique line passing through this point and the north pole, like this. And the point where this line intersects the sphere, that's the point on the sphere which we identify with this complex number. So clearly this will be a bijection of the whole plane with this sphere then, but the sphere minus the north pole, because the north pole will not be identified with any complex number. However, then it's, since we have this north pole up here, it's very natural to identify this with the point of infinity like this. You see, if we go out in the complex plane in any direction, then the corresponding points on the sphere, they will approach the north pole. So tending to have infinity in the plane is the same as tending to the north pole in this picture now. So let's see how the correspondence between these points, what it looks like. So let's say that this point has, this is a point z equal to x plus iy. And then you can also say that this point in 3 space, it will have coordinates x, y, and 0, because so we identify this plane with the plane with the plane where x3, the third coordinate, is equal to 0. Okay, so how do we put up this correspondence? Well, we have this point here, P, which is 0, 0, 1, which is the north pole, which is on this line then. And we also have this point on this point here on the line. And then, of course, the vector you get by subtracting from this point, this one, will be a vector which is parallel to the line here I have drawn. So this will be x, y, minus 1. And now we have one point on the line, and we have a vector parallel to it. So we can write down the parametric representation of this line, which then will be, if we use coordinates x1, x2, x3 here, then we see that first we get the point 0, 0, 1, and then we get t times this vector. So we get tx, ty, and here t times minus 1. So this point on the sphere, which corresponds to z, will be on this form then. So one has to determine t then, so that this will actually be a point on the sphere, which is of course just done by considering this equality then, that the sum of the squares of these numbers should be equal to 1. So if we do that, we'll get this squared plus with this squared, this can be written as t squared times x squared plus y squared. And then we get this term squared also. So if you now expand this square, then the ones here will cancel, and you can solve for t, and then you get for t that it will be equal to 2 divided by x squared plus y squared plus 1, which can also then be, this is a 2, yes, this can be written as 2 divided by absolute value of z squared plus 1. So if we just insert this expression for t here, we get the point on the sphere representing the complex number z then. We can also go in the other direction. We can, starting from a point x1, x2, x3, get the point x, y from these equations. We just note that from the last equation we see that t is equal to 1 minus x3. And then you see that here that x is equal to x1 divided by t, that is x1 divided by 1 minus x3. And similarly, y will be equal to x2 divided by 1 minus x3. So this is the way to get the complex number. This is the real part and this is the imaginary part from the coordinates of the point on the sphere. Okay, so what's the point about considering this sphere here now? Well, there are several points, but I'll start with the following idea now, that in the complex plane we have circles and we have lines. But when you project these circles or lines onto the Riemann sphere, this sphere then they will all become circles on the sphere. So why is that? Well, this is what I'll show you now. So if we take t here and insert this expression here now, and note that x is equal to the real part of z and y is equal to the imaginary part, then we get these equations here now. And then we note also that in the plane, this equation here gives a common form for both lines and circles. Why is that? Well, if a is equal to 0, and this term disappears, and what's left here is obviously the equation of a line in the complex plane then. However, if a is different from 0, then you can complete these squares here now. And then you get, in an obvious way, the equation for a circle. So this equation, so to speak, both contains lines and circles. However, if you consider the corresponding equation on the sphere by just inserting the expressions we had from for x and y, remember that x is equal to x1 divided by 1 minus x3, and y is equal to x2 divided by 1 minus x3. Then if you insert this into this equation, we get what we have here now. And then we note that on the sphere, of course, we have that x1 squared plus x2 squared plus x3 squared is equal to 1. So x1 squared plus x2 squared can be written as 1 minus x3 squared then. And this can be factored according to the conjugate law as x, well, 1 minus x3 times 1 plus x3. And then this factor will cancel out one of these factors down here. And if you then multiply this equation by just 1 minus x3, then you get this equation, which is obviously a linear equation for x1, x2, and x3. And if you consider, so this is really a plane in 3 space, and if you intersect this plane then with a sphere, of course you get a circle on the sphere. As you may have noticed, I'm cheating a little bit here now because, of course, this equation may not represent either a line or neither a line or a sphere. It could also actually be that it represents a point. If these constants are all 0, for example, then and a is different from 0, this will just be the origin. On the other hand, it's clear that this bijection we have, it will map points to points. So a point up here corresponds to a point on the sphere also. So apart from that, of course, all lines and circles in the plane will correspond just to circles on the Riemann sphere. Okay, so one way of seeing how natural it can be to consider maps on the Riemann sphere instead of in the complex plane is to consider the map which takes the complex number z to the number 1 over z. So what will this correspond to on the Riemann sphere? Well, remember these are the equations we have for the point corresponding to z. So let's now write down the point corresponding to 1 over z, which I denote in this way. So this will really be then 2 times the real part of 1 over z divided by 1 over z absolute value squared plus 1. And this will be 2 times the imaginary part of 1 over z divided by 1 over z absolute value squared plus 1. And down here then we'll get 1 over z absolute value squared minus 1, and here down here the same thing with the plus sign then. And then we remember, of course, that the real part of 1 over z, if you just multiply numerator and denominator by z conjugate, then you see that the real part of this will be the same thing as the real part of z conjugate divided by z absolute value squared, which is, of course, equal to the real part of z divided by z absolute value squared. And similarly for the imaginary part now. This will be, by the same computation, this will be equal now to minus the imaginary part of z divided by z absolute value squared. The minus sign because you have taken the conjugate here, of course. So then we can rewrite this as 2 times real part of z divided by z absolute value squared, and then the whole thing divided by 1 over z absolute value squared plus 1. And then we can multiply here now by z absolute value squared. And what do we get? Well, we get 2 times real value of z, and then divided by 1 plus z absolute value squared. And then we've compared with what we have over here, we see that it's actually the same expression. So this is equal to x1 then. So the conclusion is that this map does not change the first coordinate. The first coordinate of the image point 1 over z is the same as the first coordinate of the original point z. Here, however, we get more or less the same thing, but remember we have a minus sign here now. So if we do this computation, we will get minus 2 times the imaginary part of z divided by 1 plus z absolute value squared, which is equal to minus x2. So this map will change x2 to minus x2 on the sphere. And if we take the third coordinate here, we see if you just multiply by z absolute value squared, we get 1 minus z absolute value squared divided by 1 plus z absolute value squared, which is then equal to minus z absolute value squared minus 1 divided by same thing here with a plus sign, which is then equal to minus x3. So not only the second coordinate here of the point changes sign, but also the third coordinate changes sign. So you get plus, minus, minus. So on the sphere, we can really identify this map with a map which takes the point x1, x2, x3 to the point x1 minus x2 minus x3. So what kind of map is this? Well, if you think about it and remember linear algebra, you see that this is just rotation around the x1 axis by 180 degrees. And the conclusion we can draw now in connection with these lines and circles is that, of course, the conclusion is that this map will always map circles on the Riemann sphere to other circles, because that's exactly what this linear map does. It maps circles on the Riemann sphere to circles on the Riemann sphere. And since we know that circles on the Riemann sphere correspond to lines or circles in the plane, the conclusion is that this map will map a line or a circle to a line or a circle. But of course, there are also examples where you actually map a line to a circle and a circle to a line. In fact, if you take a circle in the complex plane which passes through the origin, it will be mapped by this map onto a line then. Okay, this can now be generalized in a very nice way. So we consider not just this map taking z to 1 over z, but we consider a more general class of maps which are called Möbius transformations. So a Möbius transformation looks like this. Where you have to assume that A times D minus B times C must be different from 0, because otherwise this will just be constant. This is called a Möbius transformation. And as it turns out, it's very natural to consider a Möbius transformation to be a map on the Riemann sphere. In a sense, it's much more natural than to consider it to be a map of the complex plane onto the complex plane, because if you consider this to be defined on the complex plane, you see that you will get exceptional points here now. As a map from on the complex numbers, it's not defined when z is equal to minus d divided by c, because then you get a 0 here. But as a Möbius transformation, you just say that if you consider the Möbius transformation on the Riemann sphere, this is just the point that maps onto infinity then. And likewise, if you want to know what the Möbius transformation does with the point at infinity, then you see that, well, if you imagine this number to be infinitely large, then you can neglect these terms and then cancel this large number, and you get that this must be equal just to a divided by c. So actually, a Möbius transformation like this can be considered to be a continuous map of the Riemann sphere onto itself. It's actually a bijective map of the Riemann sphere onto itself. And in a sense, these are the Möbius transformation. They are, of course, not the only such bijective continuous maps, but they have additional properties that makes them unique now. And the last conclusion I want to draw now is that all these Möbius transformations, they have the same property as the inversion map taking Z to 1 over Z, that they will map lines and circles in the plane to lines and circles. And of course, to prove this, it's easy to consider the corresponding statement on the Riemann sphere, which is then just that saying that a Möbius transformation takes a circle on the Riemann sphere to a new circle on the Riemann sphere. So why is that? Well, it's simply because we can consider a Möbius map to be a composition of several trivial steps. So let's start by Z then, this number. And then we map this onto C times Z. And this you may think of just as a map in the complex plane. Of course, this map is just a dilatation, so it obviously takes circles to circles and lines to lines. And then, next step, you map this this number to C times Z plus D, which is just translation in the plane, which of course also takes lines to lines and circles to circles. But these are sort of trivial steps, but here comes the essential step now. In the next step, you'd map this number to 1 over C times Z plus D. So this is really applying the inversion map. And this is really what we already have proved now, that if you consider this map to be a map on the Riemann sphere, then we know now that it will map circle and lines to circle and lines. Circles and lines. And then after this, you can just continue by trivial steps here now. In the next step, you multiply this by the factor b minus a times d divided by c. And then in the last step here now, you just add the constant a divided by c. And then you get this expression. And if you now just compute what this is by putting on a common denominator, you will see that this will be equal to C in the denominator C times Z plus D. And up here you have to multiply by Z plus D divided by C. And then you have these terms also then. And if you now you see that this term will cancel out this one, and you're just left with this simple Möbius transformation then. So the conclusion is that since every step here in this chain of mappings will conserve the class of circles and lines, the whole map taking Z to this expression, that is our original Möbius transformation, will conserve the the set of lines and circles in this sense.